Hi, let us solve some questions from the chapter radiation in this video. The important concepts and the important formula related to this chapter will be told in this video only. Okay, so let's solve the first question. It's a zero point 0.5 meter square plane gray diffuse opaque surface with this is not D, this is alpha. What is alpha? That is absorptivity. Is maintained at 500 degrees Celsius with an irradiation of 10,000 watt per meter square. Okay. Determine the total energy leaving the surface per unit area. So it's given that it's a plane gray surface with area zero point 0.5 meter square. Okay. And alpha is absorptivity. What is absorptivity? You must have studied that. The fraction of radiation energy absorbed by this plate. So alpha is 0.7. It's an opaque surface, so transmissivity will be 0. Transmissivity, this is 0. Okay. So the energy that is coming is either absorbed or transmitted or reflected back. Okay. And you must have studied that alpha plus rho plus tau is equal to 1. That is absorptivity plus reflectivity plus transmissivity is equal to 1. Absorptivity is fraction of energy absorbed by the body. Reflectivity is fraction of energy reflected by the body. And transmissivity is the fraction of energy transmitted by the body, which in opaque body's case is 0. Okay. So the irradiation, what is irradiation? The energy falling on that surface. This is 10,000 watt per meter square, represented by G. Okay, so G is 10,000 watt per meter square. And this body is at a temperature of 500 degrees Celsius. That is 500 plus 273. That is 773 Kelvin. You have to take temperatures in Kelvin in radiation. Okay, always remember this. So this body is at 773 Kelvin. That means this body will also be radiating some heat to the atmosphere. Okay. Let that be E. That is emissive power. Emissive power. Okay. And as absorptivity is given to you, transmissivity is 0. This is 0. Absorptivity is what? 0.7. So that means some part of energy falling on this body is reflected back. So that means the energy that is reflected back, let it be rho into G. Okay. What will be rho? That implies rho from here is 0.3. So 0.3 into G, that is 3000 watt per meter square is reflected back. Okay. Now tell me, what is radiosity? Radiosity is the total energy leaving the surface per unit area. Okay. So this is radiosity. So the question has asked us to find radiosity. And what is radiosity? This is sum of emissive power plus rho g. That is the energy which is reflected back. Okay. So radiosity is the total energy leaving the surface. That is in this case E plus rho g. How can you find emissive power? Basic radiation expression formula that you learn, which is sigma epsilon A T raised to the power 4. Okay, plus rho g. Rho g is 0.3 into 10,000, that is 3,000. But this is in watt per meter square. Okay, and this is in we have put this expression in watt. That means if you take E is equal to sigma epsilon A T raised to power 4, you take A below this E, that implies this is emissive power per unit area, which is sigma epsilon T raised to power 4. Okay, so that means this expression should be sigma epsilon T raised to power 4. Okay, so this is emissive power per unit area now. Per unit area. Okay, you have to balance the units, right? And also we have been asked that the total energy leaving the surface per unit area, that is watt per meter square. This is in watt per meter square. So now find this emissive power per unit area, which is E by A, which is sigma is 5.67 into 10 to the power minus 8. What is this? This is Stefan Boltzmann's constant. Sigma epsilon. Now what will be epsilon? You must have studied Kirchhoff's law. That at a certain temperature, absorptivity is equal to emissivity. That is a good absorber is a good emitter also. So alpha is equal to epsilon for a same temperature. Okay, for a same temperature. This is by Kirchhoff's law. That a good absorber is a good emitter. So alpha is 0.7. Yeah, it's given to you 0.7. And T is 773. Yeah, 773 raised to the power 4. You have to put the temperature in Kelvin only. This will be equal to, this is 14170.953 watt per meter square. Okay, so total radiosity, that implies radiosity will be this 1 plus rho g, which is 3000. So this implies the final answer is 17170.953. Units are watt per meter square. Okay. The question in the units, the units were not mentioned, but the answer, you have to give the answer in watt per meter square. So this was about radiosity. Next question. Next question is, a small sphere of outer area 0.6 meter square is totally enclosed by a large cubical hall. Okay. So a small sphere of outer area, that is its surface area is given. Radiation is a surface phenomena. Okay, so the area that you will be using is surface area. So this is a large cubical hall. Okay, and a small sphere of outer area 0.6 meter square is placed. Area of this. Okay, this is given. So I'm not writing it. It's totally enclosed by a large cubical hall. Okay. The shape factor of hall with respect to sphere is 0.04. What is shape factor and how it is denoted? It says that shape factor of hall with respect to sphere. Let sphere be body 1 and the cubical hall be body 2. Okay. So what happens that the radiations will be going from surface 2 to surface 1. Okay. And shape factor is denoted by FMN. You must have studied this, which is fraction of radiation energy going from or falling from going from body M to N. So in this case, this statement means the shape factor of hall with respect to sphere. That is shape factor of Hall with respect to sphere. That is the fraction of radiation energy going from Hall to that sphere is F21, which is 0.004. It is 0.004. This is the typing error. It's 0.004. Remember the data. So this is 0.004. What is the measure of internal side of cubical hall? Okay. So whenever this type of questions come in the question, which involves the use of shape factor and the use of area, you always have to use two theorems that you must have studied. The first one is the summation rule. Summation rule. And the second one is the reciprocity theorem. Reciprocity theorem. Okay. Mostly the questions will be solved by these two theorems or rules only. So what is this summation rule? This states that for a body 1 F11 plus F12 plus F13 up to number of bodies, let it be n, is equal to 1. Suppose there are n bodies. This is one body. Okay. This is second body. This is third body. This is fourth. And there are many n bodies. Okay. So this is 1. This is 2. This is 3, 4. And this is n. So it says that the fraction of radiation energy falling from 1 to 2, from 1 to 3, from 1 to 4, from 1 to n is equal to 1. This is the summation rule. Okay. Now what about reciprocity theorem? Reciprocity. Suppose there are two bodies. This is body number 1 and this is body 2. Okay. So what it states that obviously the radiation from 1 will be going to 2 and the radiation from 2 will be going on 1. Okay. So it says that A1 F12 is equal to A2 F21. That is, A1 is the surface area of first body, F12, the fraction of radiation energy going from 1 to 2 is equal to the surface of the multiplication of surface area of the body 2 and the fraction of radiation energy going from 2 to 1. Okay, this is a very important thing. This one and this one. Mostly, almost all the questions involving shape factor will be solved by these two theorems. This is n. These type of questions will be solved by these two theorems only. Okay. So I've explained you these theorems. You must have studied them also, but it's good to understand them again. Let me plug this. So now let us solve the question. Okay. So F21 is 0.004. Okay. So let us apply reciprocity theorem. Reciprocity theorem is A1 F12 is equal to A2 F21. Okay. What is A1? Okay, I am not going to change the page. I am directly seeing the data from here. So one is I have to see this because one is a sphere. Okay. So A1 is the surface area of sphere, that is 0.6 meter square. So this is 0.6 meter square. And F12 F12 is given to us. F12 means the fraction of radiation energy going from body 1 to 2. Is it given to us? No. Let it be F12 only. Okay. What about A2? A2. What is the measure of internal side of cubic hole? Internal side. This we have to find. If we get A2, we can find out the internal side of cubic hole. So let it be A2. And what about F21? F21 is given to us. That is 0.004. 0.004. Okay. So F21 is given to us. So this is the data. Now if I find out F12, I can find out A2 and that will give me the side of the cube. Okay. So I have to find F12. Now what I can use? I can use summation. Summation. Which says for body 1, F11 plus F12 is equal to 1. What is F11? F11 is the radiation, the fraction of radiation energy going from body 1 to falling back on body 1. Okay, so that is F11 plus F12. See here, in this case, do you think any radiation going from this surface will fall back on body 1? Any radiation leaving the surface of body 1 will fall back on body 1? No. So can I say that F11 in this case is 0 and that gives me F12 is equal to 1. See? Enlarge it. Okay. Any radiation, this is a sphere. Any radiation, from any portion, will it be going back to the body 1? No, it won't. So that means F11 is 0. Okay. Also, for a plane surface, F11 will be 0 because from any point, the radiation leaving from any point will not fall back on this plane surface. So for a plane surface also, F11 will be 0. So now F12 is 1. So that means 0.6. 0.6. This is 1 is equal to A2 0.004. So that implies A2 will be A2 comes out to be 150 meter square. Okay. And A2 is what? The surface area of cube, which is 6a square. What is A? Let it be the side of the cube. So 6a square is equal to 150 and that implies A is equal to 5 meter. That is the side of the cubical hole. So 5 meters C is the answer. So for a sphere, that is for a convex surface, F11 will be 0. For a plane surface also, F11 will be 0, but not for a concave surface. See, this is the concave surface. Let it be body 1. Okay. So the radiation leaving from this surface can fall onto this surface. See, this goes here. Okay. So for a concave surface, F11 will not be equal to 0, but for a convex surface like a sphere, F11 will be 0, and for a plane surface also, F11 will be 0. Okay. Let's move on to the next question. The next question is, a 3 centimeter diameter painted copper sphere is suspended in a large room where the walls and air are at 20 degrees Celsius. 3 centimeter diameter painted copper sphere is it is a sphere of very short, very small diameter, is suspended in a large room where the walls and air are at 20 degrees Celsius. If the emissivity of the sphere is 0.9, the emissivity of the sphere is given, which is 0.9. Determine the rate of change of temperature of sphere. Determine the rate of change of temperature. Rate of change of temperature. That means dt by d small t. Rate denotes time and dt is the change of temperature. Okay, this is how you read the statement. When its temperature is 200 degrees Celsius. Determine the rate of change of temperature when the sphere's temperature is 200 degrees Celsius. Okay, and you have to give the answer in degrees Celsius per second. Okay. So, this is a large cubical hall, and the 3 centimeter diameter sphere is placed here. So, can I say when this sphere is at 200 degrees Celsius, it will be radiating heat to the hall? Okay. Since no information is given about heat transfer coefficient, so we will be assuming that the heat is going out by radiation only. Okay. But the air in this room and the walls are also at 20 degrees Celsius. Okay. So if the heat transfer rate is taking place in the form of radiation from 1 to 2, that means if the walls of a cubical hall are at 20 degrees Celsius, that means some radiation will be taking place from 2 to 1 also. Okay. That means they will be exchanging the radiation heat. Okay. You get it? It is at some temperature to 200 degrees Celsius. The walls are also at some temperature 20 degrees Celsius. That means they will be exchanging the heat through radiation. Okay. And for that, you must have studied one expression that Q net between the two bodies is given by sigma T1 raised to the power 4 minus T2 raised to the power 4 upon 1 minus epsilon 1 A1 epsilon 1. I will explain what this is. However, you must have studied this. But I will explain this. A2 epsilon. This question is, however, a special case that you study when a small object is placed in a very large enclosure. This is a special case. Okay, but the formula for every special case you can derive by this expression. You need not learn any formula for any special cases. You can derive the formula for any special case by this expression only, which you have studied, which you must have derived while studying heat transfer. Okay. So the net radiation exchange between the two bodies is equal to sigma T1 raised to the power 4 minus T2 raised to the power 4. This is Stefan Boltzmann's constant. Sorry. This is T1 is the temperature of first body, T2 is temperature of second body. Epsilon 1 and epsilon 2 are the emissivities of body 1 and 2. A1 and A2 are the surface areas of body 1 and 2. And F12 is what? F12 is the view factor. Okay, that is the fraction of radiation energy going from 1 to 2. You can write here A2 F21 also. Why? Because by reciprocity theorem, A1 F12 is equal to A2 F21. Okay. So this is a special case, and you can derive the expression of the net radiation heat exchange between the two bodies when first body is very small in size and is kept in a large enclosure. Okay. So can I say that A2 is much greater than A1? Okay. Because it's given that it is suspended in a large room. This was the keyword. Okay. So if I multiply this whole equation by A2, this is A2. Okay. Sorry, multiply this whole equation by A1. Because multiplying this whole equation by A2 will lead us nowhere. So multiply and divide this equation by A1 and A1. So this A1 gets cancelled out. Here will also be A1 and here will also be A1. Okay. So this will be A1 and oh no, this will not get cancelled out. Sorry. So this is A1. A1. Okay. Yeah. So now are you being given have you been given with the emissivity of the sphere? Yes, you have been given with the emissivity of the sphere, that is 0.9. Okay. So epsilon 1 is 0.9. Okay. You can write here that epsilon 1 is 0.9. Okay. And what will be F12? F12 is what? The fraction of radiation energy going from body 1 to 2. This is a sphere, that is a convex surface. So F12, can I say that F12 will be 1? Why? Because all of the radiation energy leaving from 1 will eventually fall on 2, which is Q. So F12 is what? 1. Okay. Let's simplify this on the next page. Q net 1 2 is equal to sigma T1 raised to the power 4 minus T2 raised to the power 4. Here it was A1 upon 1 minus epsilon 1 by epsilon 1 plus 1. Okay. This is 1 by F12. F12 is 1. So this will be 1. Plus A1 by A2. 1 minus epsilon 2 by epsilon 2. Now nothing is given about epsilon 2, and we don't need it also. Why? Because A2 is much greater than A1. This term becomes 0. Okay. A1 by A2 becomes 0, so this term becomes 0. Okay. Further simplified, Q net 1 to 2 is equal to A1 by 1 by epsilon 1 minus 1 plus 1. This gets cancelled out. This epsilon goes up. Q net between 1 and 2 is equal to sigma A1 epsilon 1 T1 raised to the power 4 minus T2 raised to the power 4. This becomes the expression for the special keys. See, you don't need to learn them, okay? You can actually derive them. And it's a very basic derivation. You just need to remember this, that A2 is much greater than A1. Obviously, it's given that the sphere is enclosed in a very large one. Okay. So now every data is given to you. And this sigma is 5.67 10 to the minus 8. A1, area of sphere is given. Yes, we can find it out by 4 pi r square. This will be area of sphere will be 4 pi r square. Remember, this is diameter, okay? So r will be 1.5 centimeter. Put it in meters. Okay. Epsilon 1 is 0.7. No, 0.9. 0.9. This is 0.9. T1 is what? T1 is 200 degrees Celsius. That is 200 plus 273. That is 473 Kelvin. And T2 is 273 plus 20. That is 293 Kelvin. So you can find out the net radiation heat exchange between the two bodies and equate it to what? Equate it to the rate of heat lost by the sphere. Okay. That is why I was finding this term. Okay, so where should I write this? Let's rub this. So now, what the question says, that the rate of change of temperature of sphere when its temperature is 200 degrees Celsius. Okay. So can I say that the rate of heat lost by the sphere will actually be equal to the net rate of radiation exchange between the two bodies. Okay, and how can I write the rate of heat lost by sphere? This will be m uh, m Cp dt by d small t. This is dt is temperature change. This small dt will correspond to that rate part. Okay, and this should be with a negative sign. Why? Because the temperature is going to decrease. The sphere's temperature is going to decrease. Okay, this will be equal to q net, which we have found out. Okay, we have found out because we have all the values, sigma, epsilon 1, and the temperature values and area also. Okay, so the rate of heat lost by sphere is equal to the rate of net radiation exchange between the two bodies. So what is m? Mass of the sphere is not given to you, but we have been given with density, and we have been given with the diameter. So minus rho into volume, which is 4 by 3 pi r cube. R will be 1.5 centimeters. Put it in meters. Cp is given to you. Put it in joule per kilogram Kelvin. And dt by small dt. This you have to find. And you must be knowing the value of q net 1. Okay. So when you solve it, when you will be solving it, you will get dt by small dt is equal to minus of what will be the answer? Minus 0.121 degrees Celsius per second. That is why I was finding out this expression, because you see now the rate of heat lost by the sphere will be equal to the net radiation exchange between the bodies. The rate of net radiation exchange between the bodies. This is in watt. So this has to be in watt. This term has to be in watt. Okay. So this will be the answer. So the next question is, for a thin copper plate, total emissive power is given as 80 watt per meter square. The emissive power is given to you for a thin copper plate. Okay. Emissive power is given. That is E is given, capital E. Irradiation is 190 watt per meter square. That is the radiation which is falling on this plate, G, is equal to 190 watt per meter square. If this plate has reflectivity 0.6, absorptivity 0.1, and transmissivity is equal to 0.3, that means see 0.6 plus 0.1 plus 0.3 is 1. So alpha plus rho plus tau is equal to 1. Then the radiosity in watt per meter square is. Okay. Radiosity you have to find. What is radiosity? Radiosity is the radiation energy which is going out of the surface. Okay. So this E is going out. Great. When this irradiation will be falling on this surface, what happens? Some of it will be absorbed because alpha is given to you. Some of it will be reflected back, which will be rho g. Okay. Some of it will be transmitted because transmissivity is also given to you. This will be tau g. So now what you will do, that radiosity is equal to E plus rho g. Okay, and you will solve this. Because you have always studied that radiosity is equal to E plus rho g. But this is wrong. Radiosity is the total amount of radiation energy leaving through the surface, and it will be equal to let me rub this. It will be equal to plus tau g also, because this portion is also leaving from the plate. Okay, so this will be radiosity in this case. Now you can solve this. E is what? E is 80, and rho is 0.6 g. G is what? 190 plus tau. Tau is 0.3, 190. Solve it. You will get radiosity is equal to, the answer will be what? 251 watt per meter square. This was nice question again. Next question. Next is the net heat transfer Q12. The net heat transfer Q12, that is net heat transfer. That is the radiation heat exchange between surface 1 and this surface 2. This or this. Both ways. Okay. Net radiation heat exchange. If T1 is 427 degrees Celsius, that is 427 plus 273, that is 700 Kelvin. Change it in Kelvin here only. And T2 is 227 degrees Celsius plus 73, that is 500 Kelvin. And both surfaces are black. That means the emissivity of 1 and 2 is equal to 1. Emissivity of 1 and 2 is equal to 1. That is epsilon 1 is equal to epsilon 2 is equal to 1 or black. Using the following figure with the F16 is given to you and F13 is given to you. Okay, what is this 6 surface? 6 surface is the summation of surface area of 3 plus 2. And what is this 5? 5 is the summation of surface area of this 1 plus 4 surface. Okay, so A1 plus A4 makes A5 and A2 plus A3 makes A6. Okay, so now you have to find that Q1. Okay. So I've studied only one formula for Q12. That is what? That is sigma T1 raised to the power 4 minus T2 raised to the power 4 upon 1 minus epsilon 1 A1 epsilon 1 plus 1 by A1 F12 plus 1 minus epsilon 2 A2 epsilon 2. You know that this is what? This is surface resistance, this is also surface resistance, and this is space resistance. I forgot to tell you in that last question, but this is, these two are surface resistances and this is the space resistance. Okay. And how they come, this you must have studied in your theory class. Okay. So now both the surfaces are black. So 1 minus 1, this term becomes 0. Epsilon 2, 1 minus 1, this term also becomes 0. Take this above. Q12 will be sigma A1 F12 T1 raised to the power 4 minus T2 raised to the power 4. Okay. Now tell me what is missing from this equation. Okay. Sigma we know. A1. What is A1? This is 1. So A1 is 3 into 4. That is 12 meter square. 3 into 4 meter square. Okay. This we know. F12. I don't know F12. F12 is the fraction of radiation energy going from surface 1 to 2. That is this portion. Let me make it more clearly. So the fraction of radiation energy going from 1 to 2. Can you see from the figure that some part of radiation energy will be going from 1 to 3 also? Yes. But no part of radiation energy will be going from 1 to 4. This is not possible. That's plane surface, okay? So it will be going from 1 to 3 and from 1 to 2, but not from 1 to 4. Okay? And there is some data given to us which is F16 is equal to 0.093. That means the fraction of radiation energy going from surface 1 to surface 6 is 0.093. Okay, and 6 surface comprises of the surfaces 2 and 3. That means F16 is basically F12 plus F13. Okay, that is F16 is the summation of the radiation energy going from surface 1 to 2 plus the fraction of radiation energy going from 1 to 3. Okay. And F13 is given to 0.04 is F13, so I can find out F12. which is 0.093 minus 0.04. That will be 0.053. So this will be 0.053. Okay. Now you have everything. Solve this. Q12 is 5.67 into 10 to the power minus 8 into 12 meter square into 0.053. I don't remember the temperatures. That are 700 and 500. So 700 raised to the power 4 minus 500 raised to the power 4. Put the temperatures in Kelvin only. So this is which units you have to find the answer. Q12. The units are not given. They must be watt. Okay. So the options are given. So kilowatt. So this will give you the answer in watt, which will be equal to 6404640.467 kilowatt. Oh, sorry, watt. Watt. That means 6.404 kilowatt. This was the question. Okay. Let's move on to the next question. A metal sphere of surface area is given. Is an evacuated enclosure whose walls are held at a very low temperature. Okay. The temperature is not given to you. That means the temperature is not sufficient to radiate heat. Okay. The temperature of the wall is not sufficient to radiate heat. That means. Okay. So electric current is passed through resistors embedded in the sphere, causing electrical energy to be dissipated at the rate of 75 watts. So this is the electrical energy which needs to be dissipated. If the surface sphere surface temperature is measured to be 560 Kelvin, while in steady state, the reflectivity of the sphere surface is. Very simple question, just based on the energy balance. Because in this case, the wall temperature is very low, so I can definitely say that the electrical energy that needs to be dissipated is just equal to the heat radiated by the sphere. Heat radiated by the sphere. It will not be a radiation exchange now. Why? Because the wall temperature is very low. So heat radiated by sphere is what? Is actually the electrical energy which needs to be dissipated. Needs to be dissipated. To be dissipated. That is given to you. Dissipated. That is 75 watt, and this is what? This is sigma epsilon A T raised to the power 4. This is also in watts. This is also in watts. So sigma is 5.67 into 10 to the power minus 8 into what is this epsilon? Epsilon we don't know. That is we have to find out. A is 0.0225 and T is what? T is 560 raised to the power 4. If I get epsilon, I can get reflectivity. Why? I'll show you why. Epsilon is what? Epsilon comes out to be 0.598. 0.598. Okay. And this is an opaque body. I don't have space, so I have to solve it here only. So this is an opaque body that implies alpha plus rho plus tau is equal to 1. Opaque body, that means tau is 0. Okay. And alpha is equal to epsilon by Kirchhoff's law at that single temperature. That temperature. So epsilon is 0.598. So alpha is 0.598 plus rho is equal to 1. Find rho. Rho is what? 1 minus 0.598. That is 0.402. Many of you students, what will they do? They will find epsilon and they will take 0.598. They will forget to find reflectivity. So be careful. This is the answer. Next is again based on shape factor. So what you have to find? You have to find the shape factor F11. Okay, see this question. From this surface 1, this is the surface 1. This hole is the surface 1. Okay, and this is surface 2. This is surface 2, which is base, circular base. Okay, and this is surface 1. So can you see that the fraction of radiation energy goes from 1 to 2, and from 1 to 1 also, falls back on 1 also. Okay. So that is why F11 will not be 0 in this case, will not be 0. Okay. Use summation rule and use reciprocity theorem. First of all, use reciprocity theorem. I have to find F11. Okay. But reciprocity theorem states that A1 F12 is equal to A2 F21. And in summation rule, I will be getting F11, which is F11 plus F12 is equal to 1. Okay. Okay. So I need to find out F11. And is there any information given about F12? What is F12? F12 is the fraction of radiation energy going from 1 to 2. No, it is also not given. Okay, let's move on to the reciprocity theorem. What is A1? A1 is the curved surface area of cone, which is pi RL. Okay, A1 is pi RL. L is what? L is this slant height. This you can find out because this is 15, this is 15, and this is what? This is 5. So 15 square plus 5 square under root, this will be L, and L will be I don't have L, but I told you how to get that. So A1 is pi R. Okay, I know R, I know L, so I know A1. This I know. Okay. What about A2? A2 is this circular base. So I know A2 also. How? Because diameter is given, so the area of a circle is pi by 4 d square, and d is what? 10 centimeters. 10 centimeters. So I can find out I can find out A2 also. This is A2. F21. So I know A2 also. What about F21? What about F21? Can I say that F21 is 1? That is, all the radiation energy leaving from surface 2 will be falling on 1 only, because this is a plane surface. This is a plane surface. It's a plane surface. Okay. So all the radiation energy going from 2 will be falling on 1. You can also apply summation rule on 2. That will be F21 plus F22 is equal to 1. So F22 will be 0. What is F22? The part of radiation energy leaving 2 and falling back on 2. That is 0. That's not possible here. So all the energy leaving from the surface 2 will be going on 1. That implies F21 is 1. This is 1. So I know this F21, I know A2, I know A1. I can find out F12. Great. So you have to use the summation. In this question, you have to use the summation rule on both the surfaces. Okay. So F12 is what? F12 is, when you solve this, F12 will come out to be 0.316. 0.316. Okay. Put this where? Put this here. In this summation rule, applied on surface 1. You will get F11, which will be equal to 0.683. That is option what? C. 0.67. So approximately this is equal to 0.7. So F11 is 0.68. This is how you solve the questions related to shape factor, and you can expect questions related to this topic in the examination. Okay. So we'll solve some more questions related to radiation in the next video. Okay. Thanks.